Good evening. We live in exciting times and so much happening out there. And our main guest tonight is Professor David Southwood, Director of Science for the European Space Agency. But first of all, with Chris Lintott, we have some interesting newsletters, beginning with Mars. And the two American probes, Spirit and Opportunity, are now moving around, sending back amazing pictures. This one is from Opportunity.
That's right, and that outcrop there is really significant. They got very lucky. It's exactly what a geologist would want to see. You've got rock on the surface, which you could go up and look, and that's exactly what Opportunity's been doing.
But I think the main point here, we now be very sure that Mars was once a watery world. There were oceans there, and they lost it for some time.
That's right, we see that from the type of minerals that we see in the rocks, and from these strange features that are called vugs, those small pits in the surface of the rock, where minerals once formed and then have dissolved back into the ocean. You see that on Earth, you're confident that that's an old ocean bed, and we make exactly the same deduction on Mars.
So there were oceans upon Mars.
And they stayed for long enough to form rocks.
And also that showed that the conditions there were suited for life to appear. The point is, did it? That's what we don't know. What we hoped Beagle 2 would tell us. But of course, there may well be water not far below the surface. We've got to wait and see on that one.
That's true, and Spirit and Opportunity are carrying on. Spirit's actually travelled much further than Opportunity and has actually been drilling into the rocks and getting a closer look. So when you take all the results together, we're getting the most detailed geological picture we've ever had of the red planet.
And from above, Mars Express, sending back amazing pictures.
That's right. It's a resolution we've never had before. Each pixel on these images is 10 metres, which is incredible detail of the surface.
So we wait and see now. Are we going to find any trace of life there? Well, I wonder. Now let's move out beyond the solar system to a very interesting nebula.
That's right, it's an interesting story, this. The American amateur astronomer Jay McNeil, one of our greatest planetary nebula observers, was looking at an ordinary nebula in Orion, Messier 78. And he discovered this little feature here, which was believed to be a new star actually emerging from the gas and dust that make up the nebula. We know this happens. We've seen Hubble photos of the condensations as the gas and dust begins to collapse down to form a star, but we've never seen a star actually ignite. This discovery, by an amateur, remember, caused great excitement. Orion's disappearing behind the sun, so astronomers had to scramble to follow it up.
Well, now let's turn then to a very old star, in fact, a white dwarf, the remnant of a massive star, leaving a carbon-based core, and at certain seconds, under the pressure, that carbon can crystallize.
That's right.
Done so here. We have, therefore, the biggest diamond we've ever found.
That's right, and we know it's diamond, and it's about a billion, trillion carats worth, 50 light years away in the constellation of Centaurus. Now, how do we know it's diamond? This is the new result. Well, they've discovered it's actually ringing like a bell. The shock caused when it's formed is still causing the whole thing to oscillate. And you can look at those in the same way we look at earthquakes on the Earth. We seismologists use earthquakes to find out about the Earth's interior, and we can do this with this star. And we can find out that it's genuinely a complete lump of crystallized carbon. High density, but basically the universe's largest diamond.
Certainly in our galaxy, but of course another revelation. We've now imaged the furthest galaxy ever recorded.
That's right, it's been discovered at a redshift of 10, which translated means that it's from within the first billion years of the universe. So right back when it was a tiny percentage, 3% of its present size, much further than we would have expected to see a normal galaxy. Now, how have we managed to see that far? Well, we know from Einstein that light gets bent by mass, and astronomers using the Very Large Telescope in Chile have managed to use a large galaxy cluster halfway between us and this distant galaxy as an extra lens to get extra magnification, and we see hundreds of times further than we'd be able to otherwise. So it's an interesting technique. What does it tell us about the actual galaxies? Well, they seem normal, they have stars, but they're small, and maybe that's a good sign for our theories of galaxy formation. We believe that galaxies are built up out of small building blocks which come together and gradually produce the galaxies we see today. Maybe we've seen the first of those building blocks. It's difficult to say. It's difficult to fit into the theory at the minute.
I wonder how far we're going to see, but certainly we're learning more all the time.
And we must be approaching the limit. Surely we can't have galaxies much earlier than the first billion years.
I wonder. Now then, back to our solar system. We may have two fairly bright comets in April and May, neat and linear. Of course, comets are unreliable things, but we may have two naked eye comets at the same time.
That's right. Sadly, linear, which is the best at the minute, is heading south, and when it's at its best, we won't be able to see it from here. but NEAT is coming the other way, so we should have a nice naked eye comet from that, with any luck, in the middle of May.
Meanwhile, an interesting launch. Rosetta, a probe was sent out to a comet. There have been problems here with the Ariane launcher, been postponed several times. They had to change comet targets, but Rosetta is now on its way to a comet. It'll get there in 10 years' time, so I feel that I won't be doing the sky at night then, but let's hope it's successful this time.
Let's hope so, especially after all the problems they'd had with that launch.
So we must wait and see. And now for the main part of our programme. And I'm delighted to welcome Professor David Southwood, Director of Science at the European Space Agency. Welcome to the programme, David.
It's lovely to be here.
First of all, can you give us a general roundup of what's happening?
Well, I think everybody will have noticed we've been to Mars recently, and we're just overwhelmed by the wonderful results from the Mars Express orbiter. It's really fulfilling all its promises. At the same time, we're still on our way slowly to the moon with Smart 1. That's all systems a go there.
When do we arrive there?
Around Christmas this year. So it's... but then Christmas this year is going to be a busy time, just like Christmas last year, because now Rosetta is launched. The next event we've got to start looking at is the arrival at Saturn of Cassini carrying its lander Huygens. Huygens is not going to land on Saturn. Huygens is going to land on the moon of Saturn, Titan.
And what's he going to find there?
Well, I think that's a very good question, Patrick, because Huygens is going to Titan rather than Saturn because Titan has an atmosphere. It's one of the few moons in the solar system with a very developed atmosphere. In fact, at the surface of Titan, the pressure of the atmosphere is not unlike that of the Earth. It's a bit above the pressure at the Earth, and the atmosphere is a little like the atmosphere of the Earth, but missing one critical ingredient,
right.
Oxygen. It's got the nitrogen, hydrogen, carbon, the things that are, if you like, the material you need for life, but it doesn't have the oxygen.
And on Titan, land or ocean?
We've built our little baby lander to be able to splash down or crash down. We don't know if we will land in a methane sea or on the beach. We'll find out. I hope it's the beach because I think the images will be easier to handle in those circumstances. That will happen just under a year from now, but we start the critical processes in June when we put the mothership with the Huygens probe on it into Saturn orbit, and that's on June 30th this year.
Well, now let's start near the middle, shall we? What about the Sun? The Sun has been doing very unexpected things. We have the famous 11-year cycle. Maximum should have occurred in 2000, but it's been very active recently.
You're perfectly right. On this downside of the solar cycle, as we go to what we call solar minimum, we've had far more activity than we expected. There have been very dramatic flares and explosions on the Sun that push out material in great bursts from the surface right out into interplanetary space. And with that, I'm afraid, comes some bad news for our spacecraft, because you get a lot of solar radiation, high energy radiation, that can cause problems. It can interact with the electronics on the spacecraft, and we've had to do little pieces of firefighting, if I can use the analogy, on just about every one of our spacecraft in the past autumn, whilst we lived through a very stormy time on the Sun. Even so, of course, it's nil wind that blows nobody any good. So for the solar scientists, it's been a cornucopia of exciting events.
SOHO is an amazing spacecraft. It's, after all, it's nowhere near the Earth.
No, it hangs between the Earth and the Sun, continuously staring at the Sun. So it's now giving us a sort of solar space weather forecasting.
How long will SOHO operate?
Your guess is as good as mine. It's worked well beyond its expectations, but we'll keep it going. We've had one or two minor problems, but creative people working on the mission have kept it going, and I'm not going to predict its demise for a long time.
We've had the cluster mission, the the first attempt was a disaster.
I'm afraid I still remember that sad day. But anyhow, we rebuilt the spacecraft and relaunched them, and Cluster is now performing the job it was always designed to do. SOHO was to look at the sun, and Cluster was to look at the effect on the environment of the Earth, of the sun, of the changes seen by SOHO. But Cluster now has another spacecraft flying with it, a cluster of 4 spacecraft flying in formation. There is now a 5th spacecraft that was launched just after Christmas by China. And this is the first time that we've had a cooperation with China. China asked if they could be involved in the science of Cluster, and of course we're very happy to cooperate with scientists anywhere in the world. There are going to be 2 spacecraft from China in the end. Double Star 1 was launched successfully just after Christmas, and it's up there flying around the Earth, looking at how the sun and the Earth interact with Cluster. We're very proud of this first European-Chinese cooperation in space science.
It's very encouraging, I think.
Yes, I believe so.
Then, of course, we have Ulysses. And you know, some time ago, I was standing next to Ulysses, and I could, although I didn't, I could have touched it. And that now will never come back to the Earth. It's studying the poles of the sun, which we can't really study from here, and got some very interesting results.
Yes, it's just, in fact, flown past Jupiter again. It's in a polar orbit, and it got into a polar orbit by flying past Jupiter many years ago in 1992. It's been immensely successful, and it did give us our first look at the poles of the sun.
What did it tell us?
Well, it told us, in fact, the very surprising fact that over the poles of the sun there is no solar cycle. It's you have conditions more or less as you would at solar minimum, but continuously. The so-called solar wind blows out very steadily at a very high speed. Ulysses has taught us an enormous amount. I think really it's given us this third dimension of our star. And of course, as every time you go somewhere you never had been before, you find the things you didn't expect. And it's certainly done that for us.
I think one thing is very important, obviously. We are now looking not only in visible light, but all over the whole range of the electromagnetic spectrum, from the gamma rays with integral, the X-rays, XMM Newton, visible light. Then we have infrared with Herschel, microwaves, and radio waves with radio telescopes. So now we study the entire spectrum, whereas only a few tens of years ago we were limited entirely to visible light.
That's fundamental to modern astronomy, and it's also why space is fundamental to modern astronomy, because certain parts of the spectrum you can only access from space. We can start with the highly energetic parts of the spectrum, where the most extreme events emit lots of radiation that you can't see with your eye, but we can see and detect with telescopes in space, and that's in the X-rays and the gamma ray.
Gamma ray bursters.
That's right. Those are probably the most deadly things in our universe. I hope nothing ever happens near the Earth of that nature.
What exactly are gamma ray bursters?
Well, the final death of large, massive objects which go into a final nuclear explosion. I think the key thing is, with having now a gamma ray observatory, integral, run by our agency, and an X-ray observatory, we now can start tracking the history of these events. Last year we got a gamma ray burst that allowed us within 6 hours to turn around the Newton X-ray telescope so that we could look at the same place. And what happens, of course, there's an enormous first explosion, which of course is seen first in these very intense high energy gamma rays, but then there's an afterglow, and we can look at the history of the explosion, so to speak, by looking at different wavelengths.
And finally you can actually see it.
Eventually, of course, you get the visible light that you can put together, and then I think get a full pattern looking at what is going on in each wavelength of light to deduce the atomic and nuclear processes that are at the root of the light we're seeing. It's a decoding process, and the more information we get at the more wavelengths, the more we're going to understand. So we're extremely pleased about building the bridge between gamma rays and visible light with the X-ray observatory.
We're looking back now for a long way, and of course one marvellous instrument had been the Hubble Space Telescope, looking right back to the early days of the universe. There's rather sad news about Hubble, isn't there?
Yes, I'm really very sad to say Hubble, which has been the absolute workhorse of astronomy, probably the most successful space mission ever, is now at least has, I think, a limited future. And
why is this?
It's due to the fact that Hubble was always built to be serviced regularly by astronauts. And one of the sad outcomes of the loss of the shuttle 1 year ago is that it's going to be very hard to justify sending astronauts to Hubble again, because if they went to Hubble, there is nowhere safe for them to be if they find they could not land. And there's no practical way to send a lifeboat to pick them up. Hubble will go on working. I mean, all our teams, and it's a joint mission, it's a joint program between NASA, who lead it, but us Europeans as well. All our teams are looking very hard at how to operate Hubble in a way that will maximize its usefulness and lifetime.
Until when?
Well, I don't want to be held to any date. If I can keep it going for as long as I can, I will. But 2008 is probably what we're shooting for, and it's going to give us a gap, because its replacement is going to be the James Webb Space Telescope, and we are going all steam ahead to get that up there, but it's not going to be flying before about 2011.
And what else is now in the immediate pipeline?
Well, for me, I've got Herschel also being launched in 2007, that is looking at the infrared light, light we can't see with our eyes, but it's the colder part of the universe. It's looking at formation of stars, formation of galaxies, and indeed formation of planets. And that brings me back to the solar system, and probably the mission that I have a particular fondness for is Venus Express. Venus has been rather ignored.
It has.
I have to say we're not going to find any evidence of life at Venus.
No.
It's suffered a catastrophic greenhouse effect, and the temperature at the surface is such that I think the one lander that was sent by the Russians melted.
You got some pictures back there.
Yes, yes, and indeed we also have some sense of what Venus is like on the surface from looking at, with radar through the atmosphere. But Venus Express is really going to just open, I think, a new era of Venus exploration. It has been ignored. We're very proud to be leading the way back, and we'll be there. We launch next year, 2005. It's been a very rapid program, and we should arrive in early 2006. And I'm looking forward to that immensely.
So am I. And nothing from ESA on Mercury. So far, only one probe has been past it, and only about half the surface has been mapped.
Yes, we're going to look at Mercury in some depth, and we're going with a program called Bepi Colombo, named after an Italian scientist, who first taught us how to travel through the solar system using the gravity of the planets. It's really cosmic billiards we play. But why Mercury? Well, almost Mercury is a puzzle. It shouldn't be there.
No, shouldn't.
It's too close to the sun, and moreover, some of the properties it has don't seem to fit with what we really feel planets should have.
And Hubble can't look at it.
That's right. So for us, Mercury still is very unknown, and at the same time, we need to go there. really to understand the rest of our planets. Why does this anomaly exist? For me, its really fundamental surprise is the fact it has a really quite intense magnetic field.
A large iron core.
Yes, which should have long ago should have cooled down, despite it being so close to the sun. It's a small object, it should have been cooled by now. Clearly it isn't. Clearly there still is a molten core still giving off heat. Why is that? What's going on there? We're going back to the Mercury system, cooperating with the Japanese, the first time we've done that. And we're starting the work now. We're sharing out the tasks between us and the Japanese. And we hope well within a decade to have launched off to Mercury to go back to this planet and really complete the surveying of it. But at the same time, ask some of the questions we couldn't ask last time.
And then finally, what other challenges lie ahead?
Well, I think one of the grand challenges are the planets outside our solar system. And for that, we're developing new technologies and new techniques in order to, a decade or so from now, be able to really explore from Earth orbit what is going on beyond our solar system in other planetary systems. In particular, one of the key things we're going to have to practice is formation flying, is controlling spacecraft out in deep space very precisely, their positions very precisely, so we can combine light seen by 2 telescopes or 4 telescopes in such a way as to be able to look at planets without being blinded by the stars around which they're turning.
Now, looking further ahead, what about Operation Aurora?
Aurora is a program ultimately to send people to Mars. That doesn't mean we're going to do it. It's really to start the debate in Europe. What do Europeans feel about their part in the exploration of our solar system with human beings? I think it's quite clear Europeans do appreciate doing Martian exploration, but should it be done by robots? Should it be done by people? Right. And I think that's a question that everybody can have an opinion on. You don't have to be a rocket scientist to have an opinion. And Aurora at the moment is to give a plan that would show how Europe, if it wanted to, could do it, could send people to Mars.
But surely any plan to go to Mars must be entirely international.
I heartily echo those sentiments. I think truly international. I think it's not Europe and the United States. It's Europe, the United States, China, Japan, India. All of the spacefaring nations might want to look into how we could do, as a planet, a trip to our neighbouring planet.
I feel we've got to work together on that. If we don't, we won't get there, and we won't deserve to.
I think, Patrick, that's a very good way of thinking about it.
Well, we've learned so much in a very exciting time, and I feel the years ahead are going to be even more exciting.
I tell myself that all the time, Patrick. Really, for me, it's a magical period. I never dreamt when I was a schoolboy that I would be sitting here talking about the things we've been talking about.
No, it's amazing. David, thank you very much indeed.
Thank you very much.
I want to come back next month. Something totally different. We're going down a mine. There's a reservoir right at the bottom to look for dark matter. Till then.